Hello everyone, I welcome you all for the week 10 session for this tutorial for the course of Principles of Signals and Systems. So, yeah. So, let's start with today's content. So, before going ahead and solving some good amount of questions, let us first recap whatever was introduced and discussed in this week 10. So week 9, the Fourier analysis for discrete time signals was started, and in week 10, the major focus was on solving some examples on Fourier series and Fourier transform, and the concept of discrete time Fourier transform and discrete Fourier transform both were introduced. In this week, I'll majorly cover the questions which are related to DTFT, and in the coming week, that is week 11, I'll cover majorly, most of the questions will be based on discrete Fourier transform, and after that, in the last week, I'll cover the system realizations, that is the week 12 topic. So let's start with the content revision. So the discrete time Fourier transform is basically defined for a discrete time signal. Is defined for a discrete time signal, and suppose I have a discrete time signal xn, then its Fourier transform, its discrete time Fourier transform is given by x of omega, which is calculated as summation n running from minus infinity to infinity xn e power minus j omega n, and its inverse Fourier transform or inverse equation or inverse DTFT is given as xn is equal to 1 upon 2 pi integration over a period of 2 pi or over a range of 2 pi, interval of 2 pi, x of omega into e power j omega n d omega. So this is the Fourier transform equation, and this is the inverse DTFT equation. The next thing that was discussed regarding this was the convergence of DTFT, and the DTFT converges if xn is...
Hello, madam. Are you displaying the screen? Sharing the screen?
Yes, I am sharing the screen.
Okay, maybe some problem from my side. Okay, madam.
Can I just get a quick feedback from other people if my screen is visible or not?
Visible for me.
Yeah, okay, thank you. Okay, so this DTFT converges if this xn is absolutely summable, that is summation n running from minus infinity to infinity, magnitude of xn is less than infinity. Next thing that was discussed was its relationship with Z transform. We know that the Z transform is given as xz is equal to summation n running from minus infinity to infinity xn z power minus n. Now if I substitute z equal to e power j omega, then this will reduce to summation n running from minus infinity to infinity xn e power minus j omega n, which means that xz z transform at z equal to e power j omega is equal to x of omega, and this is true only if unit circle is included in ROC. R equal to 1 is in ROC. That is the region of convergence. After discussing the convergence, the next thing that was discussed was the properties of DTFT. So the first property that was discussed was periodicity. So this DTFT is periodic with period 2 pi. So it is periodic with period 2 pi. Now suppose the next property that was discussed was linearity property. So suppose x1 of n have a Fourier transform as x1 of omega, and x2 of n has DTFT as x2 of omega. Then linearity property says that a1 x1 of n plus a2 x2 of n will have a Fourier transform as a1 x1 of omega plus a2 x2 of omega. The next property that was discussed was time shift property. So it says that if x has Fourier transform as x of omega, that is capital X of omega, then Fourier transform of x of n minus n naught is given as x of omega multiplied by a phase shift factor, an additional phase factor, as e power minus j omega n naught. A dual of this property is frequency shift. That is, if I have modulation by a complex exponential, that is e power j omega naught n into xn, modulation with a complex exponential with the signal, then this results in a frequency shift, that is x of omega minus omega naught. The next property that we have is the conjugation property, and it says that if x of n has Fourier transform as x capital X of omega, then x conjugate of n has a Fourier transform x conjugate of minus omega. Next is the time reversal property. It says that x of minus n has a Fourier transform as x of minus omega. These were the properties that were covered in the and further more properties were covered which included time scaling and other. So let's discuss those. So this time scaling property in discrete time signal is a bit different thing. It's not like the way we have in continuous time case. So if I have a signal xn, then xmn is defined as x of n by m if n is an integer multiple of m, that is k equal to mn is an integer. Okay, and or what we can say here properly is n by m belongs to an integer. And the next thing is it is 0 otherwise. If we have such thing, then we are basically inserting zeros between them, and this results in shrinking of Fourier transform, that is xmn will have a Fourier transform as x of m omega. And note that here m is greater than 1. And it is an integer. The next thing that we are having here is the duality property. So this duality property says that if xn has a DTFT as x of omega, then x of t will have discrete Fourier series, continuous exponential Fourier series, that is CEFS, as x of minus m. So note that here x of omega is basically a continuous signal. It is this omega is a continuous variable, therefore this is basically a continuous signal along its domain, and therefore we can't find and also it is periodic, so a dual can be found with the help of continuous exponential Fourier series. And this xn to x of omega is basically a DTFT, and this x of omega, that is if I have xt, then it's continuous exponential Fourier series coefficient, its mth coefficient will be given as x of minus n. The next thing is differentiation in time. Differentiation in frequency. So it says that if I have a signal n into xn, then this will have its DTFT as j times dt omega x of omega. Next is the time differentiation property. So here time difference property. So if I consider xn minus x of n minus 1, then this will have a Fourier transform as x omega multiplied by 1 minus e power minus j omega. The next property that was covered was accumulation property. So it says that if I have k running from minus infinity to n xk, then this will have Fourier transform as x of omega divided by 1 minus e power minus j omega plus some DC factor, an impulse, by x0 delta omega. The next thing that was discussed was an important property, that was convolution in time. So if I have x1t convolved with x1n convolved with x2n, then Fourier transform of this will be x1 of omega multiplied by x2 of omega. After that, multiplication in time, if I consider x1n into x2n, then this will have DTFT as 1 by 2 pi multiplied by x1 of omega periodically convolved with x2 of omega. And next we have the Parseval's relation. So this says that summation n running from minus infinity to infinity magnitude xn square will be exactly equal to 1 by 2 pi integral over a range of 2 pi magnitude of x of omega whole square d omega. After that, LTI systems and its differential equation difference equation characterization was also discussed. This was a repeat, so I won't repeat it. Rather, we'll consider an example regarding this, which can be solved using DTFT. After discussing those things, then the concept of discrete Fourier transform was introduced. So this is another set of transform which is valid only for the signals which are finite duration. So suppose xn is a finite duration signal and it is n length, then xk is its DFT. It can be calculated as summation n running from 0 to n minus 1 xn into e power minus j 2 pi kn by n, and its inverse is calculated as 1 by n summation k running from, let me write it somewhere else, yeah, its inverse xn is calculated as 1 by n summation n running k running from 0 to n minus 1 xk e power minus j 2 pi kn by n. An important thing that this is a finite duration as well as it is a periodic thing, can be considered as a periodic thing, but both of them are basically finite duration n length sequences. Xn as well as xk both are finite duration n length sequences, and since this is an n length sequence, this particular DFT is known as n point DFT of the signal xn. Now this DFT has relationship with a discrete Fourier series and Discrete-time Fourier transform. So this discrete Fourier series coefficients ck into n is equal to xk if we consider this xn to be periodic with period n. And the relation with its DTFT is this x of k can be obtained as x of omega at omega equal to 2 pi k by n. Similar to the properties of DFT, we have the properties for this similar to the properties of DTFT, we have properties for DFT as well. So let's say that xn or x1n has n point DFT as x1k and x2n have n point DFT as x2k.
Hello, madam.
Yeah,
That xn is equal to that 1 by n k
yeah, it should be
0 to n
plus.
minus 1
Sorry.
e to the power of plus j, right?
Yeah, plus.
Yeah, that is, yeah. Okay, okay, ma'am.
Yeah, thank you. And another thing that I would like to highlight here, there is one more factor Wn, which is given as e power minus j 2 pi by n. And this is basically square root of unity, or rather not square, nth root of unity, and it is sometimes also known as twiddle factor. Okay, so let us look at the first property, so that is linearity property. So a1x1n plus a2x2n will have Fourier transform as a1x1k DFT plus a2x2k. Then we have the time shift property. So it's x of n minus n naught, and this shift is basically modulo n shift, and this will have the Fourier transform as e power minus j 2 pi k n naught by n into xk. X conjugate of n will have the DFT as x conjugate of minus k, and again this minus k is basically modulo n. Then we have frequency shift. So if I multiply in time domain by e power j 2 pi k naught n by n, then in frequency domain I'll have x of k minus k naught. This is also modulo n. Then I have duality property xn. If this has DFT as xk, then xn, this capital Xn, will have the DFT as n times x of minus k. Again this minus k is modulo n. Every shift and flip will be always be modulo n when we are dealing with DFT. The next property is the circular convolution property. So if I circularly convolve two finite length sequences, then this will be equal to x1k into x2k. Its DFT will be simply multiplication in frequency domain, and this is a very useful property if we go for its applications with respect to communication systems. Like OFDM uses this property a lot. Like it's built upon this particular thing and is very helpful and is currently being used in every systems that we are using. The next one is multiplication in time. So if I have x1n into x2n, then its DFT is 1 by n. x1k circularly convolved with x2k. So this was all that was introduced in this particular week. This week, as I mentioned earlier, I'll focus on the questions related to DTFT, and in the next week I'll solve the questions which are related to DFT, so that both of the topics are given equal importance, and after that I'll end with the system realizations in the 12th week. So let's start with the very first question. So it says that if I have a signal sorry so if I have been given a signal which is xn, which is equal to 1 for a fixed duration of minus n1 to n1. Now we need to comment whether it is a low pass or a high pass filter. So to be consistent with the notations, let's say this is some impulse response hn, and it is from minus 1, it is 1 from minus n1 to n1, and let's say that this n1 is odd. Okay. So how does the signal look? Suppose, for an example, let's say that this n1 is equal to 3. So in that case, this signal will look something like this. I have 0, 1, 2, 3, and so on, and here it is minus 1, minus 2, minus 3, minus 4, and so on. So the signal will look something like this. Okay. So this is just an example for visualizing purpose, and we need to find DFT for this signal for generalized case of N1. So let's start with the formula. So we have h of omega is equal to summation n running from minus infinity to infinity hn e power minus j omega n. Now note that this signal, this this h of omega is varying from n equal to minus minus n1 to n1. So we can just change its limits. N equal to minus n1 to n1 hn e power minus j omega n. Now basically the question that was asked was we need to comment whether it's a low pass or a high pass filter. Now visualizing or looking just at this this sequence just does not give us any information. So instead of looking at this, we can simply go ahead and look at its frequency domain representation so that we can understand what exactly is happening. Okay, so now here if we look carefully, since we have n1 as odd, this 0 we have in the center. So this I can write as h0 into e power minus j omega 0 plus summation n equal to 1 to capital N1, or n equal to 1 to capital N1 hn into e power minus j omega n, and hn here is basically 1, so it is e power minus j omega n plus summation minus n1 to n1 e power minus j omega n. This is minus 1. Yeah. So for this summation here, what I'll do, I'll replace n minus n as m. So after that, what we have here, this h0 is basically 1. So and e power minus j omega into 0 is also 1. So 1 plus summation n equal to 1 to capital N1 e power minus j omega n plus summation m equal to 1 to n1 e power j omega m. Again, this is just some running variable, so I can simply replace it by n. So what I have here is 1 plus summation n equal to 1 to n1 e power minus j omega n plus e power j omega n. I can just divide it by 2 and multiply it by 2. So this factor here is basically cos of omega n. So I can write this as 1 plus 2 summation n running from 1 to capital N1 into cos of omega n. So this is the DFT for this particular signal. Okay, now note that what we are having here is h of omega is equal to 1 plus summation n running from 1 to capital N cos of omega n. Okay, now okay, note that this n1 is an odd function. Okay, so what I can do is 1 plus summation n equal to 1 to n1 cos of omega n plus cos of omega n1. Okay, now we need to check whether this is a low pass filter or a high pass filter. So let's check at two frequencies. The first one is when this omega equal to 0. So if omega is equal to 0, then this h of 0 comes out to be 1 plus, this will all be cos 0, so it will be n equal to 1 to n1, cos 0 is 1, plus again this will be cos 0, so it's 1. So basically this is n minus 1, so this is 1 plus n1 minus 1 plus 1, that comes out to be n1 plus 1. Okay, and there is a 2 factor here. Yeah, I missed on to a 2 factor, so it's 2 into here and 2 here. Yeah, so it's basically 2n plus 1. Okay, now this is not equal to 0. Another thing that we need to check is what happens when at omega is equal to pi, and this will be equivalent to omega equal to minus pi. So this comes out to be h of pi is equal to 1 plus 2 times n equal to 1 to n1 minus 1 cos of omega pi n plus 2 times cos of pi n1. Now note that this pi n1 this pi n1 is basically this n1 is odd, which means that this pi n1 will reduce to cos of odd multiple of pi will reduce to minus 1. And if we look at this is from n equal to 1 to n minus 1. So if I have this situation, then in that case it's like cos pi plus cos 2 pi and so on. So the consecutive terms will be like 1 plus 1 minus 1 plus 1 minus 1 and so on. So in that situation this entire thing will go to 0, and what we are remaining with 1 plus 2 into minus 1, which is equal to minus 1. Now if you observe carefully this thing here, this one and this one so these are basically high, this 2n plus 1 plus 1 is a higher value compared to this h of pi. So basically it will look something like this. So if I have minus pi, plus pi and minus pi, this is 1. So it will look something like this, and then again it will repeat. So basically it's not an ideal, but it is some filter. some filter which is allowing the lower frequencies to pass and higher frequencies to suppress. So this is what we are having in this situation. Any questions at this point?
Madam, so the final answer is what? Is it low pass or?
It is not ideal low pass. It is trying to suppress your higher frequencies and enhancing your lower frequencies. It is behaving like a low pass filter. It's not an
Oh,
ideal low pass filter. And we can't say like okay, it is not zero here.
yes, yes.
Hmm.
So it is not a filter at all.
It is some sort of a filter. it,
Okay.
it is actually some sort of a low pass filter which is reducing the value of your this n this magnitude at pi plus minus pi. So basically when my n1 is very large, then in that situation this will be too high compared to this. In that situation it will be like a proper low pass which is suppressing your higher frequencies.
Okay.
Yeah.
So, as N1 tends to be large,
Yeah.
then it behaves like a low pass.
Yes. It behaves like a low pass anyway.
Okay. Okay.
So what happens if N1 is even? Like that case, we
Okay, if n1 is even, let me add one page. So let's say my n1 is -2. Yeah, I think it won't matter. It matters when we are speaking about its length. Yeah, yeah, it won't matter. It won't matter. But in that situation, the magnitude at here, like this factor, we were while calculating what happens at pi. In that situation, this component will not be there. It will always be like okay, 1 plus 2 times summation this factor. If I this n won't be there, like this there won't be any need of separating out these terms. In that situation at pi this will go to like 0 and its h of pi will be equal to 1. That will be the only difference. The difference will come only in its value at pi plus minus pi. It will be 1, but its envelope will be similar because I am anyway plotting its magnitude. So this is 1, but its phase will change. Phase will be different. Is it fine?
yeah, got it.
Yeah, okay, thanks. Okay, now let us look at another example. So here what we have been given is xp of n is a discrete periodic signal and we need to find its DTFT. So before going for this question, let us solve a simple question which considers a periodic signal as an example. So the first signal that we are having is xn equal to cos of pi by 5n and we need to find its DTFT. So we can write this as e power j pi by 5n plus e power minus j pi by 5n by 2, and we had seen that using this property this frequency shift property, or yeah, this property, this frequency shift property, we know that e power j omega n xn leads to x of omega minus omega naught, and we know that this delta omega, this delta t, delta n, I'm sorry, this delta omega, some constant, let's say 1, has a Fourier transform as 2 pi delta omega. So if I have e power j omega naught n, then this will have a Fourier transform as 2 pi delta omega minus omega naught. So we'll use this property here and try to find out the Fourier transform. So here the omega naught is pi by 5 and minus pi by 5. So we have 2 pi into delta omega minus pi by 5 plus 2 pi into delta omega plus pi by 5 upon 2, which can be written as pi delta omega minus pi by 5 plus pi delta omega plus pi by 5. Similarly, this xn is equal to sine of pi by 5 n. We can write as e power j pi by 5 n plus e power, sorry, minus e power minus j pi by 5 n whole divided by 2j. Similarly, we can, as we have done in this question, we can do it here also. So it is 2 pi delta omega minus pi by 5 minus 2 pi delta omega plus pi by 5 upon 2j, which can be written as pi by j delta omega minus pi by 5 minus pi by j delta omega plus pi by 5. Okay. So if I visualize this, how will this look? Let's do it for cos function since it is a bit easier. So this is 0, this is my omega axis, this is pi by 5, or let me say that this is pi by 5, this is minus pi by 5, this is pi, this is 2 pi. So I have an impulse here with a magnitude pi, an impulse here with a magnitude pi, and this repeats after 2 pi. So if I have something here, then here also I'll have a pi, and here also I'll have a pi. Similarly, at minus 2 pi also I will see its replicas, something like this. So this is basically a periodic function that we are having here, and this will this periodicity is available for all sort of DFTs, or all this periodicity exists for the DTFTs for all the signals that we have. Okay, now one more thing that we need to note in this example is this xn, that is this cos of omega, cos pi by 5n and the sine pi by 5n, both are periodic signal, and the tool that we have studied for frequency analysis of periodic signals is basically it's a discrete time Fourier series. That was the tool that we discussed for periodic discrete time periodic signals. But however, using the concept of DTFT, discrete time Fourier series, we can extend that to discrete time Fourier transform. So to understand it better, let us try to consider a more generalized case where xp is any discrete periodic signal, and let's say it is periodic with period n naught. So let's say that this xp of n is periodic with period n naught, which means that its angular fundamental frequency is given as 2 pi by n naught. Okay, now we know that this xp of n can be written as summation k running from 0 to n naught minus 1, or any for that matter any interval. So let me be a bit precise. K lying in any interval of length n naught, ck e power j k omega naught n, where this these ck's are discrete time Fourier series coefficients of so these are discrete time Fourier series coefficients of xp of n. Okay, now let us try to find the Fourier transform, the discrete time Fourier transform of this signal. So this is basically xp of omega, which can be written as summation k running from k in an interval of n naught, ck is a constant, and then Fourier transform or DTFT of e power j k omega naught n. Okay, and we have seen that this particular thing has a Fourier transform as an impulse with multiplied by 2 pi n naught ck 2 pi delta omega minus k times omega naught. Okay, now another thing that we observed in this example and also discussed in the properties, that this particular thing, this Fourier transform is basically periodic. So this x of omega is basically periodic with period 2 pi. So I can also write this finite sum as an infinite sum. Why? Because the ck's are also periodic with period n naught, and this Fourier transform xp of omega is also periodic with period 2 pi. So by combining these two, I can simply change this finite sum to infinite summation, which is something like this. That is k running from minus infinity to infinity ck 2 pi delta omega minus k times omega naught, and this will basically consider all the replicas from minus infinity to infinity of this omega. Is this okay? Any questions?
CK will be periodic.
Yeah, ck will be periodic. See, the ck is basically your discrete time Fourier series coefficients, right? So how do we write this ck? I'll add one blank page. Okay. So how do we write this ck? The ck is calculated as 1 by n naught summation n over a period n naught xn e power minus j k omega naught n. Okay. Now if I consider ck plus n naught, then this will be equal to 1 by n naught summation n in an interval n naught xn e power minus jk. This omega naught is basically 2 pi by n naught, so that I can write as 2 pi by n naught and basically now what we were having is k plus n naught. So it's k plus n naught into n. This I can simplify as 1 by n naught summation n in an interval n naught xn e power minus jk 2 pi by n naught n. This will remain as it is, multiplied by e power minus j n naught 2 pi by n naught n. This gets cancelled, and this is basically e power minus j 2 pi n. This I can write as cos of 2 pi n minus j times sine of 2 pi n. This goes to 0, so any integer multiple of pi and its sign is 0, and this cos of 2 pi n, that is even integer multiple of cos of pi, and its cos will be equal to 1. So this factor in red, this is equal to 1, which is equal to 1 by n naught. And if you observe carefully, this factor which is remaining here, this one is basically equal to your ck, which implies that your ck plus n naught will be equal to ck. That is, your ck's are periodic with the same period as your signal. Is this clear?
Madam, so basically, if I understand correctly, DFT is for finite length sequences. So you are extending to the infinite length Fourier series,
There is
right?
no DFT here, sir.
Oh, okay.
This is your discrete time Fourier series. These
Okay.
ck's are your
Yes.
discrete time
Yes.
Fourier series, and it
Yes.
is for periodic signals, and your periodic signals are never finite length.
Yes. 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 Yeah. So yes. So yes. CK are the coefficients, and yes. Yeah. Okay. I got it. Right.
Oh, any other question? Okay. If not, then let us go for the next question. So, this next we need to find the DTFT of a train of impulse periodic with period n naught. So, if you remember, the same thing was discussed for continuous time signals when we had done sampling of continuous time signals. So, this train of impulse is a very interesting thing that helps us in many ways. So why not look at the same thing when we are having a discrete time signal? So how does this train of impulse look? So if this is my n axis, this is 0, 1, let's say this is n naught, then 2n naught, and so on. Similarly, this is minus n naught, so this will be equal to 1 here, then it's all 0 in between, then again at n naught it is 1, then again here it is 1, again at some integer multiple of n naught it is 1, and in between it is all zeros. So this is how your train of impulse will look. Okay, so this is basically this train of an impulse, let's say, is x of n, and this xn is periodic with period and not. So if we look at our previous question that we did, yeah, this one, so we know that we can find the DTFT of any periodic signal using this formula, and what we need here is the first thing that we need here is to find this CK, that is Fourier series coefficients. So let's do that for this. So let's say I have CK is equal to 1 by n naught summation n over some interval of n naught xn e power minus j k omega naught n, and where this omega naught is basically equal to 2 pi by n naught. Now suppose I consider this interval, okay, this interval I am considering. So in this, so how does this interval look? So basically this point here is minus n naught plus 1 and this point here is 1. So if I consider from minus n naught plus 1 to 1 interval, in this entire interval, only at n equal to 0 I am having 1, another all values are 0. So this I can write as 1 by n naught multiplied by x0 into e power minus k omega naught into 0, which is equal to x naught is equal to 1, so this will be equal to 1 over n. Okay, so once we have this ck, this x of omega can be calculated as 2 pi summation k running from minus infinity to infinity ck delta omega minus k times omega naught, which is equal to 2 pi summation k running from minus infinity to infinity 1 by n naught delta omega minus k times omega naught, which is equal to this 2 pi by n naught I can write as omega naught summation k running from minus infinity to infinity delta omega minus k times omega naught. Now if we look at this x of omega naught, then this is also something very interesting. So if I have this point as omega naught, this is minus omega naught, then I have impulses of amplitude or magnitude omega naught. Similarly, I'll have it, this is my 2 pi, repeated after 2 pi, or basically repeated at every integer multiple of this k times omega naught. So it will be repeated after at every integer multiple of omega naught, which will be something like this. Okay. So again in frequency domain also I am getting a train of impulse. I hope this part is clear. Any further questions? Okay. So now let us look at the next question, and it gives us a simple equation, a simple signal, that is xn is equal to 0.5 to the power n un. So this is a simple, very simple question which we have been handling, signal which we have been handling for a long while, but still we'll use this simple signal to see how we can apply the properties of this DTFT. So the first one we'll find out from the scratch, the DTFT of this xn. I know that this is a very basic signal, but just for the sake of completeness, I'll solve it properly, and followed by that the next parts, that is 2, 3, 4. In that we'll try to use some properties of this DTFT. So let's start with the first part of this question. So it says that this XL is equal to 0.5 n un, and we need to find its DTFT, which is equal to x of omega is equal to summation n running from minus infinity to infinity xl into e power minus j omega n. This is equal to summation n equal to 0 to infinity. Since it is un, so I can just change it to 0 to infinity 0.5 n e power minus j omega n. This I can write as summation n equal to 0 to infinity 0.5 e power minus j omega whole to the power n. This is our simple infinite geometric progression, and we also know that magnitude of 0.5 into e power minus j omega is less than 1, which is equal to basically 0.5. So this is a converging sum, so this we can write as 1, since the first term is to the power 0, so it is 1 upon 1 minus 0.5 e power minus j omega. So this is the DFT, the DTFT of this signal, 0.5 to the power n into un. Now let us look at the next signal, that is n into xn. So if we look at our okay, if we recall the properties, and if we recall the differentiation in frequency property, so what we need to do is we need to recall differentiation in frequency property, and it says that if I have a signal n into x of n, then this will have its DTFT as j times d omega x of omega. Okay, now we from the previous part we know what is x of omega, and let's say this is x tilde of n, and let it have its Fourier transform as x tilde of omega. So therefore we have this x tilde of omega as j times d omega x of omega, and this x of omega we have found as 1 upon 1 minus 0.5 into e power minus j omega. So it is d omega of 1 upon 1 minus 0.5 e power minus j omega. So this is equal to j times minus 1 upon 1 minus 0.5 e power minus j omega square into minus 0.5 e power minus j omega into minus j. So this reduces to j times minus j is 1. 1 into minus 0.5 is 0.5, so this reduces to 0.5 into e power minus j omega upon 1 minus 0.5 into e power minus j omega whole square. So this is the Fourier transform of n into x of n, that is, so this n into x of n basically is x tilde n is equal to n into 0.5 n un. This is the Fourier transform of this signal. Any questions? Okay. Let us look at the next part of it. So the next part is basically x to n. And what does this x to n mean? So this x to n is basically equal to x of n by 2 if n is even. It is equal to 0 if n is odd. So to understand this even in much detail, so let us first draw how xn looks. So let's say this is n, this is my xn, and at n equal to 0 it takes value as 1. Then at n equal to 1 it takes value as 0.5, so this is 0, this is 1, 2, 3 and so on. At 2 it takes the value as 1 by 4, this is 1 by 2, Then here it takes the value as 1 by 8 and so on. Okay, now okay, now let us consider x to n. Okay, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8 and so on. So at x in n equal to 0, it is x2 of 0, which is x of 0 by 2, which is x0. So it is equal to 1 here as it is. Then at n equal to 1, 1 is an odd number, so here it will be 0. Then at 2, it is x of 2 by 2, which is equal to x1. And x1 takes the value as 1 by 2, which is something like this. Then 3 is an odd number, so it's 0. Then x4, x2 4 is basically x of 4 by 2, which is x2, which is equal to 1 by 4, which is here 1 by 4. 5 is an odd number, so 0. And x6 is 1 by 8, because it is basically x26 is 1 by 8, which is here, so this is 1 by 8. 7 is 0 and so on. So basically we are inserting zeros between two numbers. Okay, and from the properties we have seen that if I have xmn, then this has a Fourier transform as xm of omega, and here m is equal to 2, and therefore what we have is x2 of n has a Fourier transform as x of 2 omega, which is equal to our x of omega is basically 1 upon 1 minus 0.5 e power minus j omega. So this comes out to be 1 upon 1 minus 0.5 into e power minus j to omega. Any questions? Hello?
Yeah, madam, you seem not well. We feel bad. Maybe you can take rest. Maybe after 5. Okay. So
No, it's
actually,
fine.
we are feeling bad.
No,
You're not
it's
well.
fine.
Yeah.
No, it's fine. Okay, any questions do you have in this example?
Only that notation x to n is a little confusing. We thought x to n is a different sequence. Actually, x to n means it is x of n by 2. Huh? Is it?
X of n by 2, right? It is x of
Okay.
n by 2, but in general, x of n by 2 doesn't make sense when we are considering discrete time signals. So basically, you need to define what happens if n by 2 reduces to some fraction. Like for example, if I simply write x of n by 2, and suppose I have n equal to 1, then what does it mean, x of 1 by 2? This is not defined.
Okay.
Yeah, so to very properly or precisely define it, it's necessary to be like very precise with our notation, so that there is no further confusion. You're right that it is basically x of n by 2, but what happens at n equal to 1, n equal to 3, or some odd number? So it's basically taking value 0. So just I am defining, or just it is generally defined explicitly what exactly is happening. And this factor here is nothing but some notation.
Okay.
Different
Okay.
books will use different things and nothing else. So this xm is just telling me like how many zeros are getting inserted. So if my m is equal to 2, I'll insert 1 0. If m equal to 3, it will be 2 zeros. And if
Okay.
we observe carefully, it is showing a similar nature like what we have in continuous time signals. Like if my like if I have x of t by m and this m is some integer, then we know that this signal will expand in time domain. And like if this is my xt, then x of 2t will be something like this. Sorry, x of t by
Yes.
2 will be something like this.
Yes. It
Something
gets
similar is
expanded
happening here.
and gets filled in that in
Yeah,
between.
yeah,
Yes. Zeros. Yes.
yes. Now in continuous time, what happens is I know what is going to happen at 1 by 2. I know what is going to happen at every given value of t, any value of t. It is taking value in any given value of t from 0 to infinity, rather minus infinity to infinity. But that's not the case for a discrete time signal.
So, so if it expands, aliasing will not be there. Like,
No, see, this expansion is in time domain. Okay. See, it's getting expanded in time domain, but if you look at in frequency domain, your frequency domain is basically x of 2 omega. So if I consider, let me add a page. Yeah, okay. I'll consider some toy example. X of omega. Let's say it's something like this. It's not the exact one, just some toy, just to show that there won't be any aliasing. 0, then you'll have its replica at 2 pi, minus 2 pi, and so on. Okay, so let's say it's something like this. And let's say this is your omega m and this is minus omega m. How will your x of 2m look? When I'm having x of 2 omega, how will your x of 2 omega look? So let's say this is some omega dash which is equal to 2 omega, which means that omega equal to omega dash by 2. Means whatever was present at omega m will now be available at omega m by 2. Okay.
Yeah. It gets squeezed.
Yes, it
Okay.
will squeeze, it will shrink by a factor of 2, which is something like this. Okay. And also there will be one factor which is present here at plus minus pi. Because if I'm having something at 2 pi, and if I have this omega dash as 2 pi, then I'll have whatever was at 2 pi at omega equal to 2 pi by 2, which is equal to pi, which means I'll have some extra things at odd multiples of pi as well. These are known as
Yes.
images.
Yes. So basically, in time domain, if it is expansion, frequency domain, it is compression.
Yes,
Yes. And reverse.
yes.
Okay. Yeah, that makes sense. Yes.
See, you can understand it with the help of very simple example also. Like if I give you an impulse in time domain, it's a constant one in frequency domain.
Yes.
Similarly, if I have an impulse in frequency domain, it is constant in time domain. So if
Yes.
something is at only one instant, like only one instant, its frequency domain representation is entire available frequency range. Similarly, if in frequency I have an impulse which is at only one frequency, then in time it will extend from minus infinity to infinity with constant magnitude. So it's just expanding from minus infinity to infinity. Yeah.
Yes. Yes. Okay, madam. Right.
Okay. Yeah. So this is the answer for this question. So this x2 of omega is equal to 1 upon 1 minus 0.5 e power minus j2 omega. Okay. Okay. Now let us look at this fourth one. I'll try to squeeze it in this part only. Yeah. So what I have been given is x2n e power j omega naught n. So this is basically, for the fourth, it is basically frequency shift property. For the fourth one, we need to use the frequency shift property, which means that if I have xn multiplied by e power j omega naught n, then this will have its Fourier transform as x of omega minus omega naught. Here x2 of n is getting multiplied by e power j omega naught n. So x2n e power j omega naught n will have Fourier transform as x2 of omega minus omega naught, and we know that this is our x2 of omega which we have solved. So this x2 of omega minus omega naught will be equal to 1 upon 1 minus 0.5 e power minus j2 omega minus omega naught. Okay, so let me write it properly. It's not legit. x2 of omega is equal to 1 upon 1 minus 0.5 e power minus j2 omega minus omega naught. Now many times directly this thing will be asked, or something more complicated equation might be given. So what the best thing is, we need to find in which sequence the properties are getting applied. That will help you in finding your Fourier transform in much easier way, rather than getting involved in that infinite summation and getting the things complicated. So that's why these properties are helpful in this sense. Any questions in this example?
No.
Okay. So let's look at the next question then. So here we have been given a given an input-output relationship of LTI system with the help of basically your difference equation. Okay. So we have been given the impulse response, and we need to find the impulse response. We need to find impulse response and step response. So the step response means your input x of n is basically un. Okay. So first let us look at this yn, this equation, and let us try to find the Fourier transform. So we have y of omega minus 3 by 2. Okay. Minus 3 by 2. Using time shift property, it is y of omega into e power minus j omega plus 1 by 2 y of omega into e power minus j2 omega, which is equal to x of omega minus x of omega into e power minus j omega. This I can write as y of omega upon x of omega, which is equal to 1 minus e power minus j omega upon 1 minus 3 by 2 e power minus j omega plus 1 by 2 e power minus j 2 omega. This I can write as 1 minus e power minus j omega, and I can factorize the denominator as 1 minus 1 by 2 into e power minus j omega multiplied by 1 minus e power minus j omega. The numerator term and denominator term gets cancelled. So this comes out to be 1 upon 1 minus 1 by 2 into e power minus j omega. And this is your y of omega upon x of omega, which is nothing but h of omega. Which means that my impulse response will be inverse DTFT of this h of omega. And we have seen this equation previously. So this comes... this comes out as hn is equal to 1 by 2 power n un. Okay. Let me number this as equation 1. This is my impulse response. And next I need to find what is the step response. So next I need to find is step response. And for that we'll consider equation 1. So equation 1 implies that h of omega, which is equal to y of omega upon x of omega, it is equal to 1 upon 1 minus 1 by 2 e power minus j omega, which means that y of omega is equal to 1 upon 1 minus 1 by 2 e power minus j omega into x of omega. Now our x of n is equal to un, and this is equal to, this has a Fourier transform as pi times delta omega plus 1 upon 1 minus e power minus j omega. So now I can substitute it back here. So what we have is y of omega is equal to 1 upon 1 minus 1 by 2 into e power minus j omega multiplied by pi times delta omega plus 1 upon 1 minus e power minus j omega. So now if I do this, then this comes out to be 1 by pi upon 1 minus 1 by 2. Now anything multiplied by an impulse will take the value at that point. So this will be e power minus j0, which is equal to 1 into delta omega plus 1 upon 1 minus 1 by 2 into e power minus j omega multiplied by 1 minus e power minus j omega. So this is basically 2 pi 2 pi into delta omega plus, let's say, y hat of omega. So if we do that, so this y of n will be inverse DTFT of this. So this 2 pi delta omega is basically the DTFT of 1. So therefore this is basically equal to 1 plus y y hat of n. So let us try to find what is y hat of n. So this y hat of omega is equal to 1 upon 1 minus 1 by 2 into e power minus j omega into 1 minus e power minus j omega, which is equal to, using partial fractions, let's say a upon 1 minus 1 by 2 e power minus j omega plus b upon 1 minus e power minus j omega. So this I can write as 1 equal to a into 1 minus e power minus j omega plus b into 1 minus 1 by 2 into e power minus j omega. Okay. Now for finding a, let's say that this e power minus j omega is equal to 2. Then this 1 minus 1 by 2 into 2 reduces to 0. So what we have is 1 equal to a into 1 minus 2, which is equal to minus a, which means that a equal to minus 1. Similarly, to find the value of p, let's say that this e power minus j omega is equal to 1. So this a terms go to 0 and 1 is equal to p into 1 minus 1 by 2, which is equal to b by 2, which means that b is equal to 2. So what we have is a is equal to minus 1 and b is equal to 2. Then what we are having here is y hat of omega is equal to a, that is minus 1 upon 1 minus 1 by 2 into e power minus j omega plus 1 upon 1 minus e power minus j omega. Okay, so what I'll do is I'll take this factor okay. Okay, I'll take this factor back and I'll substitute it to y of omega for convenience. So this y of omega, or okay, let it be. So this I can further simplify as I can add plus delta omega and subtract delta omega term. Okay. Then in that situation, the first factor, this one, has a inverse DFT as 1 by 2 power n un, and this factor here has inverse DTFT as un, and this is basically another impulse but now with a magnitude as 1 by 2. So this I can write as minus 1 by 2 into 2 times pi delta omega. So this is basically equal to minus 1 by 2.
Madam, B is 2, right? Not 1.
Yeah,
A,
sorry. Okay, sorry. So this will be 2 and 2 here. So this will be 2 times un minus 2, minus 1. Yeah, thank you. Yeah, okay. So my yn comes out to be 1 by 2 power n un plus 2 un minus 1, which is y hat, and this factor here was plus 1 here. So this 1 gets cancelled. So it is 1 by 2 to the power n un plus 2 times un. Any questions?
Like Z transform also can be used like that.
Yeah. Z transform will be a simpler way to solve it because that won't involve this impulse and other things, handling of
Yes,
those
yes.
impulses. Z transform, Laplace transforms are easier version of like to handle these examples because unit step function ka Z and Laplace are well defined. Like they
Yes.
don't involve any impulses, so those are easy to handle. If you solve it using Z transform, you will get the same answer. Just try it out as a
Okay.
small exercise.
Thank you.
Yeah. Okay. If there are no further questions, then let us look at the next part here. Okay. So this next question says that you need to consider in the series RC circuit, and now the output is taken across the resistor. Okay. The example that was covered in the class was basically for a was output across capacitor, which reduces to basically your uh, low pass filter. But now if we consider a series RC circuit with with output across your resistor, then let's look at what happens here. So what we are having here is series RC circuit. This is my XT, which is input. And output is taken here. And we'll use Laplace transform to find its transfer function first. To find its equivalent discrete time representation if it is sampled at duration Ts. So in order to do that, first we need to find what is the impulse response, that is Ht. And for that, let us consider Laplace transform, which is a handy tool for doing the same thing. So if we do that, then Ys upon Xs can be calculated as, we can simply use the voltage division thing, that is R. The voltage across this will be R upon impedance, total impedance, that is R plus 1 by Cs. The impedance of the C is basically 1 by Cs in the Laplace domain. So this is equal to RCS upon 1 plus RCS. And we know that we have given the value of RCS 4. So I'll just substitute that 4S upon 1 plus 4S. Now what I'll do is so this is my HS. What I'll do, I'll add and subtract 1. This is 4s plus 1 upon 1 plus 4s minus 1 upon 1 plus 4s. So this gets cancelled. So it is 1 minus 1 by 4 upon s plus 1 by 4. Now this is a constant one, and we need to find what is ht. So this ht is basically, this is 1. So this is delta t minus 1 by 4 upon s. So this is 1 by 4, and we know that 1 upon s plus a will have inverse Laplace as e power minus at ut, assuming this is a causal system. Okay. So using that, this is equal to 1 by 4 into e power minus t by 4 into ut. Okay. Now we need to find h tilde n, which is equal to h of nts, which is equal to delta nts minus 1 by 4 into e power minus nts into u. NTS, which can be written as delta N note that this is basically this thing. Okay, fine. Let's write it as delta NTS minus 1 by 4 into e power minus NTS, and this u of NTS can be simply written as UN. Now note that this is delta NTS, and this N is basically samples of your test.
Madam, is it NTS by 4, right? Yes.
Yeah, sorry, NTS by 4. Yeah, thanks. Okay, yeah. Now basically this delta T was something like this. It was at 0. If I sample it something like this here, so it will persist only when my n is equal to 0, and otherwise it will go to 0. So that's why I can simply write it as n delta n minus 1 by 4 e power minus n ds by 4 into un. Is it okay? Similarly, I can find it Z transform and discrete time Fourier transform. Any questions? Okay. Now let us consider the next. Okay. So the next question says that we need to consider a discrete time signal. So basically it should be system, not signal. Consider discrete time system with DTFT as h omega equal to 1 for magnitude of omega less than or equal to omega c, and this omega c is less than pi, and it will repeat, and we need to find its impulse response. After that we need to find its finite impulse response approximation. So first let us see whether it is an infinite impulse response system or not. So for that let us find its time domain representation, that is Hn. Okay, so let us see how does this look. So this is basically my omega axis. This is 0, this is 2 pi, this is minus 2 pi, this is minus omega c, this is omega c. Similarly I have it here. So this is something like this. And so on it will repeat, and somewhere here we have minus pi and plus pi. Okay. Yeah. And this is basically my h of omega, and I need to find what is Hn. So this Hn is basically 1 by 2 pi integral over an interval of 2 pi h of omega into e power j omega n d omega. This can be written as 1 by 2 pi integral, let's say the interval is from minus pi to pi h of omega into e power j omega n d omega, which is equal to 1 by 2 pi integral. Now if I consider this interval from minus pi to pi, this is non-zero only from minus omega c to omega c. So I can write it as minus omega c to omega c h of omega, which is equal to 1 into e power j omega n d omega, which is equal to e power j omega n upon 2 pi j n from minus omega c to omega c, which is equal to e power j omega c n minus e power minus j omega c n upon 2j into 1 upon pi n. So this comes out to be, this is basically sine omega cn. This is sine of omega cn upon pi n. Now let us see, so this is valid when n is not equal to 0, otherwise this expression is not valid. So now let us find out what is h0. So h0 is 1 by 2 pi integral from minus omega c to omega c 1 e power minus j omega 0, so that is 1 d omega. So this is basically 2 times omega c upon 2 pi, which is equal to omega c by pi. Okay. So what we are having is Hn is equal to two cases, omega c by pi when n is equal to 0, it is sine of omega cn upon pi n when n is not equal to 0. Okay, is this part clear? Now if we observe this equation, n is not equal to 0 means it is ranging from minus infinity to infinity, which means that this is an infinite impulse response, that is IIR filter, and we need to find its finite impulse response approximation. So next thing that we need to find is finite impulse response approximation. That is is to find h1 of n such that, and note that this h1 of n is not equal to 0 for n belonging to minus n to n. Okay, and this h1 of n is non-zero from minus n to n, and it is equal to 0 otherwise. And we need to find this h1 of n such that the mean square or the squared error of these two over n is least. And it was seen in the lectures that this is possible, this is minimum, this error, this squared error is minimum, this error is minimum when h1n is equal to hn for n belonging to minus n to n, and it is 0 otherwise. So what we have is h1n is equal to omega c by pi when n is equal to 0, sine of omega c n upon pi n when n belongs to minus n to minus 1 and 1 to n, and it is 0 otherwise. Is this clear? Any questions? Okay. If not, then let's go ahead with the next question. Now we need to convert the low pass filter in the question 8 to a high pass filter by frequency shift, the way it was done in the class. So see, if we observe here, so in question 8 what we had was, in question 8 the low pass filter was something like this. It was 1 for magnitude of omega less than omega c, less than or equal to 2b. Okay, so it was something like this. This is pi, this is minus pi, and we need to change it, we need to convert it to a high pass filter, which is something like this. Yeah, yeah, this is minus pi, this is pi, this is pi minus omega c, this is pi plus omega c. So we need to do this, and this operation is done by introducing frequency shift of pi. So let's say this was HL of omega, and let's say this is H of omega. So this H of omega is equal to HL of omega minus pi. Okay, now consider the frequency shift property. Okay, consider frequency shift property. So what does it say? So e power j omega naught n xn will have a Fourier transform, or will have a DTFT as x of omega minus omega naught. Okay. Now here I have this HL of omega minus pi. So here my omega naught is basically equal to pi. So what I'll have is this h of n is equal to HL of n multiplied by e power j. Omega naught is basically pi, j pi n, and we know and this e power j pi n is basically minus 1 to the power n. So we have seen this previously, but I'll repeat it. This e power j pi n can be written as e power j pi whole to the power n, which is equal to cos pi n plus j times sin pi n whole whole power n. There is no n here. Yeah, and this cos pi is minus 1 to the power n. So this I can write as minus 1 to the power n h l of n. Now note that this one that we have obtained as in the previous case. So this is what we have here. So this is my HL, this HN equation that we are having here. This one is my HL. So this HH of n, so let me just repeat the thing. From the previous question, this HL of n was basically sine of omega c pi upon pi n for n not equal to omega c n not equal to 0, and it was equal to omega c by pi when n is equal to 0. And this is basically equal, and from this equation that we have obtained, HH of n is basically HH of n is basically minus 1 to the power n HL of n. So this I can write as minus 1 to the power n sine of omega c n by pi n, n not equal to 0, and this is equal to omega c by pi, since minus 1 to the power 0 is 1, for n is equal to 0. And note that this is an IIR filter, and similar to the previous example that we had here, the finite impulse response approximation for this filter was basically that filter values for the allowable range. Similarly, we'll have in this case also. So FIR, that is finite impulse response approximation, for n in a range of minus n to n is simply HH, and let's say finite FIR of n is equal to minus 1 to the power n sine of omega c n upon pi n for n belonging to minus n to minus 1 union 1 to n. It is equal to omega c by pi when n is equal to 0. It is equal to 0 otherwise. So if we look at this equation here, so this is basically HLFIR. So this I can also write as HLFIR of L. Any doubts here?
Madam,
Yeah.
madam, how can high frequency filter response is same as a low frequency filter response? H of HFIR
Oh,
and is equal.
sorry. Into minus 1 to the power n.
Yes, yes.
Any other questions?
So that means, can we make a general statement saying that any low frequency filter, if you shift it by pi, it becomes a high frequency filter?
Yes.
Okay.
See, this is a generalized diagram that I had made here,
Okay.
right? It had nothing to do with your omega c and all. So if I shift any low pass filter by a pi radians frequency, then I'll get a high pass filter.
Okay.
This can be also generalized for continuous time signals, but there we would have to be a little bit more careful. It won't be a shift by pi, but something more. Any other questions? Okay. Let us look at the last question of today's tutorial. So here I am deliberately taking the proofs of two properties of DTFT. So we need to prove the conjugation and multiplication in time property of DTFT. Okay. So first let us consider conjugation property. So let's say Xn has a Fourier transform or DTFT as x of omega, and this is equal to summation n running from minus infinity to infinity xn e power minus j omega n. Now let's say x conjugate of n has DTFT as x tilde omega. So this x tilde omega can be written as summation n running from minus infinity to infinity, x conjugate of n e power minus j omega n. Now let us take conjugates on both the sides. So what I have is x tilde conjugate of omega is equal to summation n running from minus infinity to infinity xn e power j omega n. Now this I can write as summation n running from minus infinity to infinity xn e power minus j minus omega n. Now if I compare these two things, this one and this one, so this one is basically equal to x of minus omega. Now again taking conjugate, what I have is x tilde omega is equal to x conjugate of minus omega. So this is the proof for the conjugation property for DTFT. Okay. Okay. Now let us look at the multiplication in time property. So what does it say? Multiplication in time property, x1n into x2n is equal will have a Fourier DTFT as 1 by 2 pi x1 of omega periodically convolved with x2 of omega. Okay, and this periodic convolution is over a period of 2 pi, so it is 1 by 2 pi integral from 0 to 2 pi x1 of gamma x2 of omega minus gamma d gamma. Okay.
Madam, one thing.
Yeah.
Periodic convolution means circular convolution. Both are same?
Similar.
Okay. Same, right? The word.
Same.
Yeah.
You can
Okay.
say same.
Okay.
But in circular convolution, the thing is it can be applied to a finite duration sequence. It need not be a periodic sequence.
Okay.
Yeah.
Okay.
Both the things are actually similar. Like if you consider the finite duration sequence repeated after every n times and then apply periodic convolution, it will be as good as your circular convolution.
But here it is a continuous. X1 omega is a continuous,
Yes.
right?
So I'm integrating. I'm not.
Yeah. Yeah.
Yeah.
So yeah. Okay. Okay.
Okay. So what we'll do is we'll start with RHS this side and then try to get back to LHS. So let's say this is yn. Okay. So this yn is basically equal to 1 by 2 pi integral over a range of 2 pi y of omega. This is equal to my y of omega into e power j omega n d omega. Now this I can write as 1 over 2 pi integral over 2 pi y of omega is this factor, so this I can write as 1 over 2 pi integral from 0 to 2 pi x1 of gamma x2 of omega minus gamma d gamma multiplied by e power j omega n d omega. Now I'll change the order of integration. I'll change this order of integration as 1 over 2 pi integral from 0 to 2 pi x1 of gamma into 1 over 2 pi integral over a range of 2 pi x2 of omega minus gamma d gamma e power j omega n d omega d gamma. Okay, So this is what I am having right now. Yeah. Okay. Now observe this part, this thing in green color. So this is basically IDTFT, that is inverse discrete time Fourier transform of x2 of omega minus gamma. Okay. So if x1 of n x2 of n has DTFT as x2 of omega, then x2 of n multiplied by e power j gamma n will have a DTFT as x2 of omega minus gamma using the frequency shift property. So this green thing basically reduces to x2n into e power j gamma n. So what I have now is, so this is equal to 1 by 2 pi integral 0 to 2 pi x1 gamma multiplied by x2n into e power j gamma n t gamma. Now this x2 is constant with respect to the integration variable, so I can just take it outside. So what I have is x2n then multiplied by 1 by 2 pi integral 0 to 2 pi x1 of gamma into e power j gamma n t gamma, and this factor here is nothing but my inverse DTFT of x1 gamma. So this is basically equal to x1 of n. So this reduces to x2n multiplied by x1n, which means that this y of n is equal to x1n into x2n. So we started from this RHS and then went back to my LHS. This proves the multiplication in time property. Any questions?
Madam, the 2 pi factor 2 pi disappeared. Uh, 1 minute.
This entire thing, sir, this thing.
Yes, yes.
This entire thing is the inverse DTFT of
Yes.
x2 of omega minus gamma. And this 2 pi is coming here.
Oh, okay, 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 okay. Yeah,
Which is
okay.
again
Fine.
coming here.
Yes, yes. Okay, okay. I got it.
Yeah.
Yes.
Any other questions? This was all I had planned to cover today. So if you have any questions, please feel free to ask. Otherwise, you may leave the meeting.
Thank you.
Thank you.
Thank you, madam.
Thank you.